Hi Rockridge, this is Mrs. Berger and welcome to day 2 of our Unit 7. Today we'll talk about logarithm graphs and transformations. Last time we talked about exponentials. We'll compare and contrast the two. So logarithm functions, you guys have not seen the algebra behind these, so we are just looking for you to identify and be able to declare this is a logarithm function. But logarithm functions can be identified by either log or natural log. A natural log, or ln, is still a logarithmic function and acts like it. Some examples so that you can identify these things from the algebra. You may see something like y equals log base 2 of x. So this is base 2. You may see f of x equals 3 times log base 7 of x minus 3 plus 2. That's a base 7. You may see g of x equals natural log of x plus 2. This is actually base e. E is a number like pi. It's a special number. Let's find these buttons on our calculator so that we know where to find them. So if you're looking for the log button, log by itself is this button off to the left here. That assumes that your base is 10. If you don't see a base, you assume that the base is 10. And you can find the log of any number. The log base 10 of 8 is 0.90308, and you can see that. If you're looking for natural log, once again, that is log base e. That button is right below. Natural log of 8 is 2.079. Okay. Now I know you don't know the algebra behind this. You will certainly find this out in future calculus classes, but for now, be able to find these functions in your calculator. Okay. Now let's go back and see what we've got here. The anatomy of a logarithmic function. So you'll see y equals, and they transform just like everybody else, right? A is your stretch, compress, flip, times log base of x minus h plus k. K is still in charge of your up, down. H is still in charge of your left, right. And then your base right here can be any kind of number. Typically, if it, like I said, if it doesn't have any number there at all, we assume that it is 10. So if you just see y equals log of x, we assume that the base is 10. Whereas up here in the examples, you saw a base of 2 specifically explicitly written. That means we're changing our base from a 10 to a different number. If you see ln of x, or y equals ln of x, we assume that the base is e. That is always the case with natural log. For these graphs, we have vertical asymptotes only, right? And those vertical asymptotes are of the form x equals h. Okay? So those are the opposite of what we saw with the exponentials. So let's do some more comparing and contrasting. You should know that exponential and logarithmic functions are inverses of each other. Just like when we saw quadratics and square roots, positive and negative square root, those are inverses of each other. Exponentials and logarithms are inverses of each other. So what that means is, remember what was the case whenever we have inverse functions. It means that this little invisible line here, if you're those 3D artistic types, unlike me, I'm not like this at all, but if you're a 3D artistic type and you can visualize rotating these functions over across that y equals x line, you're looking at inverses. So if you can rotate it across that line, or inverse it, or make it symmetric across that line, you're going to draw the inverse. I am more of a math, enter it and calculate it type person, so I'm going to do this algebraically. So if I have an exponential function, like on the left here, y equals, or f of x equals 2 to the power of x, let's remember what points created that function, okay? If we were to put in negative 2 for x, we would get out 2 to the negative 2, which is 1/4. We saw this in our last lesson. 2 comma 1/4, that's negative 2 comma 1/4, that's right here. If we put in negative 1, that's 2 to the negative 1, that's 1/2, and that's why 1 comma a half is on this, negative 1 comma a half is on this graph. If we were to put in 0, 2 to the 0 is 1, so that's why 0, 1 is on this graph, and so on and so forth. 2 to the power of 1 is 2, that's why 1 comma 2 is on this graph, and then 2 to the power of 2 is 4, so that's why 2 comma 4 is on this graph. Now let's jump to the logarithmic function. Mrs. Berger, you said that the logarithmic function is the flip, the inverse of the exponential. Let's watch that play out. Remember, we swap x and y values for inverses. So if negative 2 comma a fourth is on the exponential, that means 1/4 comma negative 2 is on the logarithmic. So 1/4 comma negative 2, I'm going to get close, here we go, that's on our graph. If negative 1 comma 1/2 is on the exponential, 1/2 comma negative 1 is on the logarithmic. So 1/2 negative 1. If 0 comma 1 is on the exponential, 1 comma 0 is on the logarithmic. 1 comma 0. Oh, did I mess up? I think I messed up this guy. Here we go. Sorry about that. And then if 1 comma 2 is on our graph, then 2 comma 1 is on our graph. And finally, if 2 comma 4 is on our graph, 4 comma 2 is on our graph. So we can start to see what this thing looks like, and we can confirm that it is rotated across that y equals x. So now we can see that these are inverses of one another. Let's continue the comparisons. The exponential function had an asymptote of y equals 0. The logarithmic function has an asymptote of x equals 0. Do you see that? Do you see how this x equals 0 line is what it's approaching here? On the exponential function, you have a domain of all real numbers and a range, for at least the parent graph, of 0 to infinity. For the logarithmic graph, we have a domain of 0 to infinity, at least for the parent, and a range of all real numbers, or negative infinity to infinity if you want to do the long way. So you can see they're opposites, they're inverses of each other, they're complete opposites of each other. That's to help you kind of get in the mindset of what a logarithmic graph is. So if you wanted to put in these values into your calculator, you could certainly input log base 2 of 1/4, and the calculator would spit out negative 2. So you can confirm your table of values. Or you can certainly graph this graph as well. Now let me show you where to find if you need to change the base. So let's take a look at what we just did. In y equals, we needed to have log base 2 of x, right? So let's take a look at that. If we go to the math menu, down here in choice A is log base. If you need to change your base from 10 or E, the main home buttons, you can do log base, and you can change that to your log base 2 of x, and you can graph that. Now, something I caution you on using your calculator, because of the way the calculator works, it will cut off your values and it'll make it look like it stops. We know from doing this graphically that this thing will approach and go down forever, right? It does not stop here. The problem is it gets smaller and smaller from an x value and the calculator has a hard time with it. So when you look at this, don't let it trick you. Don't let it tell you that it stops there. It actually just continues to approach that y-axis forever and ever and ever. You can see here when you do a table of values on this function how it errors. It errors out at 0. If you were to put in 0, it would be an error. And so you just need to know that anything to the left of that, it's just going to continue to approach that 0 forever and ever and never actually get there. Okay. When you do it on Desmos, it actually doesn't cut it off for you. So if you were to go to Desmos and put in this function here, it would not cut it off for you. So let's see, y equals, and then you can go to your functions and find your log function. Log. Now let's go ahead and do log base 2 just for fun. So we'll do a log base 2 of x. And if you look, it actually does not cut it off for you. See how it just gets closer and closer? It doesn't cut it off for you like the calculator does. So that's one advantage that the desmos.com/calculator has over and above our calculators. So in any case, we see how these things act. They have vertical asymptotes instead of horizontal. We'll want to find the reference point for logarithms. Now remember, for exponentials, it was 0, 1. So what do you think the logarithm reference point is going to be? Yep, just the opposite, 1, 0. Okay. So you'll want to find the vertical asymptote. And that'll just be x equals h. We'll grab that first, so you'll look inside the parentheses to find what your vertical asymptote is. That'll be a huge guiding aspect of the graph. And then your reference point, you'll start at 1, 0 and shift left, down, up, right, skinny or widen. And then if the base ends up being something other than 10, if you would like, you can always do a table of values. So you can make yourself a table of values and just invert them or flip them. So you can find the exponential values and then flip them to get the logarithmic values, or type it in the calculator to find those values. For the most part, you are likely going to use your vertical asymptote and your starting point as your main aspects of it, and then just get as close as you can using values, because you don't have the algebra understanding of what logs are to do any further than just translating. Okay. So let's jump into translating some of these and sort of take away the mysticism behind them. Applying transformations to logs works the same way as it does with exponentials. Your A is in charge of flip, stretch, compress. Your H is in charge of left, right. And of course we change the sign for that. And your K is in charge of up, down. Don't forget that your reference point, your original reference point, is 1, 0. So let's launch right into these. When we look at number 1, there's an invisible 1 for the A, so there's no flip, stretch, compress. For the H value, it's 2, and for the K value, it's 0. Our reference point of 1, 0, let's see what happens to it. It doesn't get flipped or stretched. It does move right 2, so 1, 2, and it doesn't move up or down. So our new reference point here is 3, 0. And you can certainly put that in your calculator if you want to do log base 2. Let's do that now. Let's go to our home screen and do math, choice A. Do log base 2 of, what was our value? Of 3 minus 2. So you can do 3 minus 2. And it has 0. So whenever you need to check your values, you can do this in the calculator. You can compute that. Just make sure that you go to the math menu if you need to change your base from a 10 or an E. Alright, so we've confirmed that that's on there. Now our asymptote on the parent graph is right along here. It's x equals 0. The stretching of the A value doesn't do any stretching or compressing. The H value moves it 1, 2 to the right. So you'll move it to the right. And then an up-down, I mean, there is no up-down on this one, but if it was to shift up or down, that would have no impact, because moving a vertical line up or down, it has no impact, right? So our new asymptote is x equals 2. Okay, so we use all of this to clean up this graph here. We use all of this to graph our function as best we can. You can grab some more values off of your table, but our domain on this, we don't go any further left than 2, and we'll go forever to the right. Our range is all real numbers, forever down, forever up. We are increasing from 2 to infinity. Remember, the life of this, it doesn't go any further left. And increasing, decreasing is in terms of x values. So it's increasing from 2 to infinity. There is no left-end behavior. This graph does not go forever to the left. So we don't write as x goes to negative infinity because x doesn't go to negative infinity. On the right, as x does go to positive infinity, f of x goes to positive infinity as well. It will climb slowly but surely up to infinity. Let's take a look at number 2. This one, once again, we don't have any shift of the a. H, there's no left-right. K, there is a down 3. So the original starting point of 1, 0 will not be stretched or compressed. It will not move left or right. It will move down 3. 1, 2, 3. So our new value is 1, negative 3. So that's our starting point. Our original asymptote was x equals 0. The a value doesn't do anything to it. The left-right, nothing happens left-right. And down 3, moving that line down 3 really doesn't change that line itself. That doesn't have any impact. So we still have an asymptote of x equals 0. And so this function approaches 0 here and goes that way. The domain is from 0 to infinity. The range is all real numbers. That's true of all log functions. Even though that calculator cuts it off, it really does go forever down and forever up. And it is increasing from 0 to infinity. There's no left end. And on the right, as x goes to infinity, f of x slowly but surely goes to infinity. For number 3, once again, we have no flip, stretch, or compress. We have a left 1, up 2 scenario. And so the impact this has on our starting point is we will go left 1, up 2. So our new starting point, reference point, is 0, positive 2. Our asymptote on the original graph is x equals 0. The a has no impact. The h moves it to the left 1. And the k value up 2 really has no bearing. So really it's just the left 1 that has an impact on this asymptote. So we're going to graph that asymptote at x equals negative 1. X equals negative 1. And there's our starting point. And so this graph approaches here and it looks like it levels out, but it continues very slowly up. Our domain starts at negative 1 and goes to infinity. Our range is all real numbers, as it is with all logarithm graphs. We are increasing for the entire domain, that domain only being from negative 1 to infinity. There is no left end. It just never goes to negative infinity on the left. On the right-hand side, as x goes to infinity, f of x also goes to infinity. Now, on number 4, remember, if we don't have a base, we assume it to be 10. So if you're putting this into your calculator and need to understand some of the points, remember that you can either use that home button, or you could, if you wanted to, you could do the math menu in the log base, but it would be a log base 10. So if there's no base there, it's a log base 10. Now, this function has no a in front of it, so it's just an invisible 1 again. It is not being shifted left or right. It's not being shifted up or down. Our reference point is still 0, 1. It's not being shifted at all. Our asymptote is still x equals 0. So even though that base changed, the asymptote and the starting point, the reference point, are still the same. It will play out slightly differently in the rise of that right-hand side. You can grab some values off your calculator if you need to. But this is the view of this graph. So our reference point is 0, 1. I'm sorry. 1, 0. Our reference point is 1, 0. Our asymptote is x equals 0. Our domain is 0 to infinity. Our range is all real numbers, which is true of all log graphs, whatever their base. We are increasing for the entire domain of this function from 0 to infinity. There is no left end. And on the right-hand side, as x goes to infinity, y goes to infinity slowly but surely. Let's take a look at our challenge problems. In this case, we have an a of -1 that will have some impacts. We have an h of 2 and a k of 4. So if our starting point is 0, 1 on our parent graph, if we negatize the y value of 1, 0 is 0. So if we multiply 0 times -1, it's still 0. So that a value has no impact. If we move to the right 2 and up 1, 2, 3, 4, we land at 3, 4. So 3, 4, oops, is our starting point. And our asymptote, it used to be at x equals 0. If we negatize that, that has no impact. There's no y aspect of a vertical asymptote, so that doesn't have an impact. If we move right 2, however, it does have an impact. So our new vertical asymptote is x equals 2. Of course, an up-down shift of 4 has no impact because shifting a vertical line up or down really doesn't have any change. Our domain, and of course this thing approaches here, oh, I apologize. We'll talk about how that looks. It will approach there. Let's take a look at what this does look like on the graph so you can see. Negative log of x minus 2 plus 4. Now notice that we didn't have a specific base on there, so we are assuming the home button version, which is a base 10. So when we type it into y equals, this is what it looks like. Don't forget, the calculator is going to cut it off errantly. It does not actually look like that, but let's look at the graph. Notice that instead of going up, up, up slowly, it's now going down, down, down slowly. And so that vertical asymptote of x equal 2, you can see where that is. And then that graph should continue to skirt along the edges of that line, x equals 2, but it doesn't. The calculator is cutting it off. If you were to put this in Desmos, it wouldn't cut it off. So what this looks like is it's approaching here, and then it's slowly approaching like this. It's probably more dramatic than it actually is. But this domain, now once again, our domain is from 2 to infinity. That really doesn't have a huge impact with the negatization. The range of this is still all real numbers, which is true of all log graphs. But now we are decreasing from 2 to infinity. There is no left-end behavior because it doesn't go to negative infinity. It just continues to approach that 2. And then as x goes to positive infinity, y is going to go down eventually to negative infinity this time. Okay. And if you need to pull a table of values off your calculator to help make that a little prettier, you can go second table. Just know that it will error out for quite a few. As it approaches that asymptote, it's going to be an error world for a while. It just has a hard time with values that close. So come on down away from that asymptote value of 2 to get some decent values. They don't have to be perfect. If 12, 3 is off the graph, don't worry about it. Just get as close as you can with these decimals so you can have a clear sense of what this graph looks like by hand. Let's look at our last example here. Now remember, natural log or ln of x plus 2, that means log base e, that special number. You'll learn more about that in future classes. Our a value for this is 1. There's nothing else out front. So our a value for this is 1. Our h value is 0. Now remember, this is like this, okay? So unless you see parentheses around x plus 2 altogether, this is how you should assume the transformations are happening. That's very important. And then k value is up 2, right? Positive 2. So if our original reference point was 0, 1, I'm sorry, I keep saying that. It's 1, 0. If our original reference point was 1, 0, Multiplying that y value of 0 by 1 does nothing to it. We're not shifting left or right, we are shifting up 2. So our new reference point on this graph is 1, 2. Our asymptote was x equals 0. Let's put that in temporarily. If we multiply the y value, well, an asymptote doesn't have a y value, so we can skip the impact of a. The left-right shift doesn't happen, and the up-down shift has no impact. So our x equals 0 asymptote remains. So let's just clean this up a little bit and put so let's leave our x equals 0 asymptote and graph our reference point. You can certainly graph other points off of our calculator, but this is basically what it looks like. Our domain is 0 to infinity. Our range is all real numbers. So notice, even with that weirdo base of e, the transformations happen the exact same way. So don't let that natural log scare you. And then increasing, decreasing, we are increasing from 0 to infinity. We have no left end. And on the right, as x goes to infinity, f of x will eventually go to infinity. Now I know it's a little bit frustrating because we don't understand the interworkings of logs, log base 10, log base 2, log base e. You will get that in future classes. What we want you to understand is how these graphs get shifted from their original states. Okay? So go ahead and try your homework and let us know if you have questions.